when some wag said it's feasible to think responsibly about one thing and not the other. Well, I could see from that one sentence that that was perfectly ridiculous. And it pushed me further into my natural drift, which was into learning all the big ideas and all the big disciplines.
Welcome to The Deep Dive. Today we're embarking on a deep dive into chemistry. It's the fundamental science that underpins basically everything around us, from the air we breathe to the device you're holding right now. You've asked us to explore the big ideas in chemistry, and yeah, we've compiled a fantastic array of sources. They break down the core principles explaining why matter behaves the way it does. Think of this as your essential guide, maybe, to understanding everything from substance properties to reaction mechanisms. And, hopefully, presented with some surprising facts and real-world relevance.
That's right. Our mission today is to, walk you through 10 core concepts. These really form the very framework of chemistry. By the end of this deep dive, you should have a much clearer grasp of that microscopic world, and how it profoundly dictates our macroscopic reality. It's pretty amazing stuff. So let's dive in.
Okay, so to truly understand chemistry, we have to start at the most foundational level, don't we? The atom. It's often called the building block of matter, but why is it so fundamental to everything that follows? I mean, really, why start there?
It truly is the starting point. At its core, atomic theory basically says that all matter, everything you can see and touch, is made of atoms. These are the smallest possible units of an element that still hang onto that element's distinct chemical identity. What's really remarkable, I think, is how unique each element's atoms are. And it's purely based on the number of protons in their nucleus, their atomic number. So, 11 protons means sodium, 17 means chlorine. That number defines the element. Simple as that.
Right. And it was John Dalton, way back in the early 1800s, who really formalized this. And we know atoms have subatomic parts, of course, but his core idea that chemical reactions are just rearrangements of these atoms, never creating or destroying them. That still holds incredibly true today, doesn't it?
Precisely. That's the conservation of matter. It's a bedrock principle. And within that atom, its internal structure is what really explains its chemical behavior. It's fascinating. Over 99.9% of an atom's mass is crammed into its dense nucleus. But it's the electrons buzzing around in specific regions called orbitals. Well, they are the real players in chemistry. Especially those outermost ones, the valence electrons.
Ah, valence electrons. Okay.
But their arrangement is the absolute key to an element's reactivity. Think about neon, a noble gas. It's incredibly stable, right? Because it has a full outer shell of electrons, happy as can be.
Doesn't need to react.
Exactly. But then you look at sodium, an alkali metal. It's highly reactive, almost desperate to get rid of that one lonely valence electron.
So that difference in electron setup dictates everything.
It really does.
The powerful insight here, it seems, is that atomic theory allowed us to move from just, observing stuff to actually designing it rationally. By understanding what's inside those seemingly indivisible units, we unlocked breakthroughs like, atomic clocks, nuclear energy.
Huge leaps forward.
It really is like understanding the alphabet before you can even think about writing a book, isn't it?
That's a great analogy, yes.
So if atoms are the letters of chemistry, then the next logical step is how these letters come together.
Yeah.
How do they form words or even entire sentences? Because most atoms aren't stable just floating around on their own, right? They like to connect. How does that happen?
They connect by forming chemical bonds. These are essentially attractive forces that hold atoms together. And they typically form because, by doing so, atoms can achieve a lower energy state. They get more stable. Often, that means completing their valence electron shells, getting that full set.
Okay, stability is the goal. And there are different ways they do this, different types of bonds.
Yeah, we generally categorize them into three main types. First, you've got covalent bonds. This is where two atoms share pairs of electrons. It's super common between nonmetal atoms. Think water, HO. Oxygen shares electrons with two hydrogens. This sharing often helps atoms get that full outer shell, following what we call the octet rule, aiming for 8 valence electrons usually. Covalent bonds create distinct molecules, with very specific 3D shapes.
And that shape matters.
Oh, absolutely. It affects properties like polarity. Water, for instance, has unequal sharing, making it a polar molecule, which is hugely important.
Okay, so sharing is one way. What's another?
Second type, ionic bonds. This is less about sharing and more about a complete transfer of electrons. Typically happens between a metal and a nonmetal. Think table salt, sodium chloride. Sodium basically gives away an electron to chlorine.
Ah, donation.
Exactly. This creates oppositely charged ions, a positive sodium ion, not O, and a negative chloride ion, Cu. And then opposites attract, right? They stick together strongly.
So they don't form individual molecules like water.
No, exactly. Ionic compounds form extended crystal lattices, big ordered structures. These attractions are really quite strong. That's why salts tend to have high melting points and can conduct electricity when they're melted or dissolved in water.
Got it. Covalent sharing, ionic transfer. What's the third type?
The third one is metallic bonds. You find these, unsurprisingly, in metals. They're characterized by what's often called a sea of electrons.
A C.
Yeah, these electrons are delocalized. They aren't tied to any single atom. They're free to move across the entire piece of metal. This unique bonding model explains why metals are such fantastic conductors of electricity and heat.
Because the electrons can move freely.
Precisely. And also why metals are often malleable. You can hammer them flat and ductile, you can draw them into wires. Think of mercury, for example. It's a liquid at room temperature because its metallic bonding is, well, unusually weak compared to other metals.
Wow. Okay, so the truly fascinating takeaway here is how the type of bond completely dictates the properties, whether something's a gas or a solid, brittle or bendy.
It all comes back to the bonding, yeah.
It's like the hidden rule book governing all material behavior. So understanding this helps us design new drugs, create advanced materials like alloys, ceramics, even just understanding why salt dissolves in water. It boils down to these bonds.
Fundamentally, yes. The interaction between the water molecules and the ions.
Okay, so atoms are letters, bonds are how they connect. What about the periodic table? It feels like the ultimate cheat sheet, or as you said, a super organized dictionary for all these elements. But what deep secrets does its organization really, reveal to us?
Well, it's far more than just a list. It's truly a masterpiece of organization. The periodic table arranges all the known elements by increasing atomic number, yes, but also, crucially, by recurring chemical properties. An element's position, its address on that table, directly reflects its atomic structure, especially its electron configuration.
It's the electrons again.
Always the electrons. The horizontal rows, the periods, they show us how electron energy levels are being filled. While the vertical columns, the groups, they bring together elements with similar valence electron setups. And that leads to remarkably similar chemical behaviors.
Give us an example.
Sure. Look at group 1, the alkali metals, lithium, sodium, potassium, down the list. They all have just one outer electron. And as a result, they're all highly reactive in similar ways.
Okay, so the position tells you a lot. For us, the power here is that because of this systematic arrangement, you can actually predict things about an element just by seeing where it lives on the table. These are the periodic trends, right? Tell us about a couple of the big ones.
Absolutely. Prediction is key. Two of the most, illustrative trends are, first, atomic size. Generally, an atom's radius tends to get smaller as you move across a period from left to right.
Smaller, why is that?
Because the nucleus is gaining more protons, pulling those electrons in tighter, more positive charge, stronger pull.
Okay.
But size increases as you go down a group. That's simpler. You're just adding new electron shells further from the nucleus. So cesium, way down at the bottom left, is a much bigger atom than lithium up at the top.
Makes sense. What's another key trend?
Then you have things like ionization energy. How much energy it takes to remove an electron, and electronegativity, how strongly an atom pulls shared electrons towards itself. These trends generally move in the opposite direction to size.
So smaller atoms hold on to electrons tighter.
Basically, yes. Both ionization energy and electronegativity tend to increase as you go across a period, left to right, and decrease as you go down a group. Think about fluorine, up in the top right corner, ignoring the noble gases for a sec. It's the most electronegative element. It really wants electrons.
Okay.
Whereas elements at the bottom left, like francium, they're the least electronegative. They give up their outer electron pretty easily. This explains that general pattern metals on the left tend to lose electrons, form positive ions, while nonmetals over on the right tend to gain or share electrons. And we see other clear trends too, like in metallic character, how metally an element behaves in overall reactivity. For metals, reactivity usually increases going down a group. It's easier to lose that outer electron from a bigger atom. For nonmetals, like the halogens in group 17, reactivity generally decreases down the group.
Wow, that predictive power is incredible.
It really is. It's why the table is so profound. Dmitry Mendeleev, who first arranged it this way, famously left gaps for elements that hadn't been discovered yet, and he accurately predicted their properties, like gallium and germanium, based purely on the trends.
Amazing.
And today, chemists use these same trends constantly to tailor new materials, design semiconductors, catalysts.
Even figuring out mineral supplements for our bodies.
Exactly. It's the unifying blueprint. It connects everything.
All right. Now, every chemical reaction, big or small, involves energy-changing hands, right?
Yeah.
This brings us to thermodynamics, the study of energy and its transformations. It seems like it tells us not just if a reaction can happen, but how energy flows between the reaction and everything else around it.
Indeed. Thermodynamics gives us the fundamental rules for energy transfer. They apply everywhere. The first law is basically the conservation of energy. You can't create it, you can't destroy it.
Only changes form.
Exactly. Energy only gets transformed. If a reaction releases energy, say as heat or light, that energy didn't just appear. It was already there, stored in the chemical bonds, and now it's changed form. When methane burns, for example, it releases a lot of stored chemical energy as heat. That energy was just transferred. We measure these heat changes using something called enthalpy. Reactions that release heat are exothermic.
Like burning things.
Right. And reactions that absorb heat are endothermic, like those instant cold packs you crack. They get cold because they're pulling heat in from the surroundings.
Like this is the first law? What about the second? That one sounds more mysterious. Entropy. Disorder.
Yeah, the second law deals with entropy. Disorder is a common way to think about it, but it's maybe more precise to call it the dispersal of energy and matter, how spread out things become. It basically explains the direction of spontaneous change. Things naturally tend to spread out, energy disperses.
Things don't spontaneously tidy themselves up.
Pretty much. For a reaction to happen spontaneously, meaning on its own without continuous energy input, the total entropy of the system and its surroundings must increase overall. Energy and matter become more spread out. This idea is beautifully tied together with enthalpy in a concept called Gibbs free energy, represented as He.
Gibbs free energy. Okay.
If the change in Gibbs free energy for a reaction is negative, then the reaction can proceed spontaneously. Think about gasoline burning. It's highly spontaneous. Why? Its exothermic releases heat, which disperses energy, and it produces lots of gas molecules from liquid fuel, which disperses matter. Both enthalpy and entropy are favorable, so Te is very negative.
Okay, so thermodynamics tells us if a reaction is possible, if it's energetically downhill, so to speak, and how much energy is involved. But I remember hearing about reactions that are thermodynamically favored but just don't happen or happen incredibly slowly.
That's an excellent point, and it leads us perfectly into the next big idea.
Yeah.
Yes. Thermodynamics tells you if it can happen and where the end point equilibrium lies, but it tells you absolutely nothing about how fast it gets there. A classic, almost mind-bending example is diamonds turning into graphite. Thermodynamically, graphite is actually the more stable form of carbon under normal conditions.
So diamonds want to become graphite.
Energetically speaking, yes. The conversion is spontaneous, Te is negative.
But they don't, thank goodness.
Exactly. Because kinetically, the speed of that reaction is practically zero. The energy barrier to get it started is just immense. It takes, well, geological timescales, effectively.
So thermodynamics says go, but kinetics says not so fast.
Precisely. And just to tie it back to bonds quickly, when chemical bonds form, energy is typically released at stabilizing. When bonds break, energy needs to be put in. So exothermic reactions often involve swapping weaker, higher energy bonds for stronger, lower energy ones and releasing that difference as heat. Endothermic reactions need energy input because they're forming, on balance, higher energy bonds.
Got it. So if we connect this to the bigger picture, thermodynamics is kind of like the energy accountant for chemistry. It tracks the energy flow in everything from those hand warmer packs to the incredibly complex metabolism in our cells processing food energy.
That's a good way to put it. Energy bookkeeping. It helps us predict and harness reactions based on their energy changes.
Okay, so if thermodynamics tells us if a reaction can happen, then chemical kinetics answers that other vital question. How fast will it actually go? And controlling that speed seems incredibly important for, well, pretty much everything. What determines the pace?
You're absolutely right. Kinetics is all about the rate of chemical processes and the factors that influence that rate, things like concentration, temperature, catalysts. And you highlighted the key link. Even a very spontaneous reaction, thermodynamically speaking, can be uselessly slow if the kinetic barriers are too high, like that diamond example.
So what is reaction rate exactly?
It's simply a measure of how quickly the concentration of reactants decreases or how quickly products form over a specific time period. Some reactions are blazingly fast, almost instantaneous. Think of an acid mixing with a base. Neutralization happens in a flash.
Like,
Others are incredibly slow, like iron rusting. That takes days, weeks, years.
so what makes the difference at the molecular level? Why are some fast and some slow?
It comes down to collisions. For molecules to react, they first have to collide.
Okay, makes sense.
But not just any collision works. They have to collide with the right orientation lined up properly and, crucially, with enough energy. This minimum energy needed for a reaction to occur upon collision is called the activation energy, often written as E.
Activation energy, like a hurdle they have to jump over.
Exactly like a hurdle.
Ah.
A high activation energy means a high hurdle. Only a few molecules will have enough energy to make it over at any given time, so the reaction is slow. Like trying to burn a big log, you need a match, a spark, to give those first molecules enough energy to get over the hump. A low activation energy means a low hurdle. Lots of molecules can clear it easily, so the reaction is fast. Like sodium metal reacting explosively with water, very low E.
Okay, so activation energy is key. What else affects the rate? Temperature.
Oh, absolutely. Temperature almost always speeds up reactions, often dramatically.
Why is that?
Two reasons, really. Higher temperatures mean molecules are moving faster, so they collide more often. But more importantly, they collide with more energy. A larger fraction of the molecules will have enough energy to overcome that activation energy barrier, EE.
So more collisions and more successful collisions.
Exactly. That's why food spoils much faster on the counter than in the fridge. The cold slows down those spoilage reactions.
And why a glow stick glows brighter in hot water, the reaction speeds up.
Precisely.
What about how much stuff you have? Concentration.
Yep. Concentration and pressure matter too. Higher concentration of reactants means there are more molecules packed into the same space.
So they bump into each other more often.
Right. More frequent collisions generally lead to a faster reaction rate. For gases, increasing the pressure squishes the molecules closer together, which is basically the same as increasing concentration. So gas phase reactions usually speed up at higher pressure. Think about wood burning. It burns much faster in pure oxygen than in regular air, where oxygen is only about 21%, higher concentration.
Okay. And what if one of the reactants is a solid?
Good question. For reactions involving solids, surface area becomes critical. If you increase the surface area that's exposed to the other reactants, you greatly speed up the rate.
How so?
Because the reaction can only happen at the surface where the reactants meet. More surface means more places for collisions to occur. That's why iron filings rust way faster than a solid iron nail, much more surface area exposed.
Or why powdered sugar is way more flammable than a sugar cube.
Exactly. Powdered sugar has enormous surface area, so it can burn incredibly fast, potentially causing a dust explosion. A sugar cube burns much more slowly.
Okay, this is making sense. But you mentioned catalysts earlier. They seem like a way to cheat the activation energy hurdle, right? How do they work their magic?
Magic is a good word for it sometimes. A catalyst is a substance that dramatically increases the reaction rate without being consumed in the process itself.
It doesn't get used up.
Nope. It participates, but it gets regenerated. They work by providing a completely different reaction pathway, an alternative mechanism. And this alternative pathway has a lower activation energy, a smaller hurdle.
So it doesn't remove the hurdle, it just finds an easier way around it.
That's a perfect way to think about it. Catalysts don't change the overall thermodynamics. They don't make an impossible reaction possible or change the final equilibrium position. They just help the system get to that equilibrium much, much faster.
Like enzymes in our bodies.
Exactly. Enzymes are nature's catalysts. They are incredibly efficient, speeding up biochemical reactions by factors of millions, even billions. Life as we know it wouldn't be possible without them operating on those millisecond timescales. Industrially, catalysts are vital too. The iron catalyst used in the Shaber process to make ammonia for fertilizer. Without it, the reaction would be far too slow to be practical, even though it's thermodynamically favorable.
Wow. Okay, so the ability to control reaction rates kinetics is just fundamentally crucial. In industry, it's about efficiency, making enough products quickly and safely. In medicine, it dictates how drugs work, how fast they react in the body.
Absolutely. Drug metabolism, drug action, all kinetics.
And in biology, enzymes ensure life happens fast enough.
Yeah.
Even everyday things, like putting food in the fridge to slow spoilage or using heat to cook food faster, that's all applied kinetics.
It really is.
So kinetics is truly the clock of chemistry. It lets us manage time, essentially tailoring conditions for everything from making plastics to preventing rust.
Well said. The clock of chemistry. I like that.
All right. Now, many chemical reactions, maybe most, are reversible. They can go forwards and backwards. This brings us to chemical equilibrium. It sounds static, like things stop, but you said earlier it's dynamic. What does that really mean?
Yeah, equilibrium can be a misleading word. Chemical equilibrium isn't a state where everything stops. It's a dynamic state reached in a reversible reaction when the rate of the forward reaction becomes exactly equal to the rate of the reverse reaction.
Rates become equal, not amounts.
Exactly. The rates balance out. So reactants are still turning into products, and products are still turning back into reactants, but they're doing so at the same speed. The result is that there's no net change in the overall concentrations of reactants and products. They stay constant even though the molecules are constantly reacting back and forth.
Can you give an analogy?
Sure, think about water in a closed bottle. Some water molecules are always evaporating from the liquid surface to become vapor. At the same time, some water vapor molecules are condensing back into the liquid. At equilibrium, the rate of evaporation exactly equals the rate of condensation. So the amount of liquid water and the amount of water vapor in the space above it remain constant. It looks static, but molecules are constantly jumping between phases.
Okay, that helps. It's a balance of opposing processes. And you mentioned earlier there's a way to quantify this balance, the equilibrium constant, K.
Yes, exactly. The equilibrium constant, K, gives us a specific number, a ratio, that tells us the relative amounts of products and reactants present at equilibrium for a given reaction at a specific temperature. A large value of K means that at equilibrium, the products are heavily favored. The reaction proceeds mostly to completion.
Lock of products, few reactants left.
Right. A small value of K means the reactants are favored. At equilibrium, you'll still have mostly reactants, with only a small amount of product formed. Take that Haber process again, making ammonia. N plus 3 H's, 2 NH. Even at equilibrium, the mixture will always contain some unreacted nitrogen, N and hydrogen, H's. K isn't infinitely large. So equilibrium doesn't mean you have equal amounts of everything. It just means the ratio defined by K has been reached, and the net concentrations aren't changing anymore.
Got it. It's about the ratio staying constant. Now, what happens if you have a system at equilibrium and you poke it, you disturb that balance? This is where Le Chatelier's principle comes in, right? It sounds like the system fights back.
That's a great way to put it. Le Chatelier's principle states that if you take a system already at dynamic equilibrium and you apply a stress, like changing the concentration, pressure, or temperature, the system will shift its equilibrium position in a way that counteracts or relieves that stress. It tries to get back to a balanced state, albeit a new one.
Okay, how does that work? Let's take concentration first.
Sure. If you change concentration, say you add more reactant to a system at equilibrium, the stress is too much reactant. The system counteracts this by shifting the equilibrium forward, consuming some of that added reactant and producing more product until a new balance is reached.
Makes sense. Use up what was added.
Conversely, if you remove a product, the stress is not enough product. The system shifts forward again, making more product to replace what was removed. Industries use this cleverly. In the Haber process, they continuously remove the ammonia as it forms. This pulls the equilibrium constantly to the right, forcing more nitrogen and hydrogen to react.
Smart. Like tricking the equilibrium.
Kind of. In our bodies, too. When your cells use up oxygen during metabolism, the equilibrium of oxygen binding to hemoglobin in your blood shifts. Hemoglobin releases more O to the tissues where it's needed. That's Le Chatelier in action.
Wow. Okay, what about pressure? You mentioned that for the Haber process.
Right. Changing pressure mainly affects equilibria involving gases. If you increase the pressure on a system, usually by decreasing the volume, the stress is too much pressure. The system will shift its equilibrium toward the side of the reaction that has fewer total moles of gas molecules. Fewer gas molecules exert less pressure.
Ah, okay, so Haber, N euro plus 3 arrows, that's 4 moles of gas, goes to 2 NHs, only 2 moles of gas.
Exactly. So increasing the pressure pushes the reaction towards the product side, the side with fewer gas moles, ammonia. That's why they run it at very high pressures.
Makes perfect sense. What about temperature?
Change in temperature is a bit different. It actually changes the value of the equilibrium constant, K. If you raise the temperature of a system at equilibrium, the stress is too much heat. The equilibrium will shift in the direction that absorbs heat. That's the endothermic direction.
Okay, uses up the extra heat.
And if you lower the temperature, the stress is not enough heat. The equilibrium shifts in the direction that releases heat, the exothermic direction, to try and warm things back up. So for the Haber process, which is exothermic, it releases heat. Increasing the temperature actually hurts the ammonia yield. It pushes the equilibrium back towards the reactants.
But didn't we say higher temperature makes reactions faster?
We did, and that's the trade-off. Higher temperature gives a faster rate, kinetics, but a lower yield at equilibrium thermodynamics for an exothermic reaction.
So they have to compromise.
Exactly. Industrial processes often run at a moderate temperature or compromise to get a decent rate and a reasonable yield.
Fascinating balance.
Yeah.
And what about catalysts? Do they shift the equilibrium?
No, they don't. This is important. A catalyst affects the forward and reverse reaction rates equally. It speeds up both directions. So a catalyst helps the system reach equilibrium faster, but it does not change the final equilibrium position or the value of K. It doesn't change the final yield, just how quickly you get there.
Got it. Faster, but not more. So the big insight here is really how crucial understanding equilibrium is. It governs so much, like the pH balance in our blood, kept stable by buffer systems that's equilibrium at work.
Absolutely. Bicarbonate buffer system is a classic example.
How drugs spread through the body, how industries maximize how much product they get.
All equilibrium considerations.
It explains why reactions often result in mixtures, not just pure products, and it gives us tools, like the Chatelier's principle, to manipulate those outcomes. A really powerful concept.
Definitely one of the core ideas.
Okay, let's switch gears slightly. Let's talk about two really big categories of reactions that seem fundamental. Acid-base reactions and redox reactions. They're both about transfers, right? One involves protons, the other electrons.
Exactly. They are absolutely foundational types of chemical reactions, and yeah, they govern a huge range of processes, from how we digest food and how batteries work, to how our cells get energy and why things corrode. Let's start with acid-base chemistry. The most common definition we use, the Brønsted-Lowry definition, is pretty straightforward. An acid is a substance that can donate a proton, which is just a hydrogen ion, He, and a base is a substance that can accept a proton.
Proton donor, proton acceptor.
Right. A classic example is hydrochloric acid, HCl, reacting with sodium hydroxide, NaOH, which is a base. HCl donates its H to the hydroxide ion from the NaOH.
And they form water.
Exactly. Hate plus OO makes H-arrow. That's a neutralization reaction. It's worth noting that in water, that proton H doesn't really exist on its own. It latches onto a water molecule to form the hydronium ion, H-arrow. But we often just write H for simplicity.
Okay. And water itself can be involved.
Yes, water is really interesting. It's amphoteric. Amphoteric. It means it can act as either an acid or a base, depending on what it's reacting with. This ability of water leads directly to the pH scale, which is just a convenient way to measure the concentration of HO ions and therefore the acidity of a solution.
Right. pH 7 is neutral, lower is acidic, higher is basic.
Precisely. So stomach acid is very acidic, maybe pH 1 or 2. Household ammonia is quite basic, maybe pH 11 or 12. And acid strength matters too. We talk about strong acids and weak acids.
What's the difference?
It comes down to equilibrium again. A strong acid, like HCl, dissociates almost completely in water. It gives up basically all its protons. A weak acid, like acetic acid, the acid in vinegar, only partially dissociates. It sets up an equilibrium where most of the acid molecules remain intact and only some donate their protons. We quantify this with an equilibrium constant called Ka, the acid dissociation constant.
Okay. And this weak acid equilibrium is important.
Hugely important. It's the basis for buffer solutions. Buffers are typically mixtures of a weak acid and its corresponding base partner. They have this amazing ability to resist large changes in pH when you add small amounts of other acids or bases.
Like the buffer in our blood you mentioned.
Exactly. Our blood pH has to stay in a very narrow range, around 7.4. Buffer systems, like the bicarbonate buffer, are essential to maintaining that stability. Life depends on it.
Wow. Okay, so that's proton transfer. What about the electron transfers? Redox.
Right, redox chemistry. It's short for oxidation reduction. In redox reactions, it's all about the movement of electrons. One substance loses electrons. We call this oxidation.
Oil oxidation is loss. I remember that one.
That's the one. And another substance must gain those electrons. That's reduction. RE reduction is gain.
And they have to happen together, right? You can't have one without the other.
Always, always together. Electrons have to come from somewhere and go somewhere. A simple example. If you put a piece of zinc metal into a solution containing copper ions, like copper sulfate, The zinc metal loses electrons, it gets oxidized, becoming zinc ions. Those electrons are immediately picked up by the copper ions, which gain electrons. They get reduced, turning into solid copper metal.
So zinc gives electrons, copper takes them.
Yep. And we have terms for the roles they play. The substance that gets oxidized, zinc in this case, is called the reducing agent because it causes the reduction of the copper ion.
Ah, it enables the reduction.
Right. And the substance that gets reduced, the copper ions, is the oxidizing agent because it causes the oxidation of the zinc.
Okay. Oxidizing agent gets reduced, reducing agent gets oxidized. It's a bit confusing.
Takes a second to get straight, yeah. Just remember what's happening to the electrons. Oxygen itself is a very common, very powerful oxidizing agent, hence the name oxidation.
Right. So where do we see redox reactions? Are they common?
Oh, incredibly common. They are everywhere. Combustion burning fuel, whether it's wood, natural gas, or gasoline, that's rapid oxidation. Corrosion, the rusting of iron, is the oxidation of iron metal. Cellular respiration, how our bodies get energy from glucose by reacting it with oxygen, is a complex series of controlled redox reactions.
Our bodies run on redox.
Fundamentally, yes. And photosynthesis in plants is essentially the reverse process, using light energy to reduce carbon dioxide back into sugars. Batteries, every battery, from the tiny one in your watch to the big one in your car, is a carefully designed redox system. Chemical energy is converted to electrical energy via spontaneous redox reactions.
Wow.
Even things like bleaching clothes with chlorine bleach or disinfecting surfaces, those involve strong oxidizing agents that break down unwanted molecules or kill microbes via redox. And antioxidants like vitamin C or vitamin E that we hear about, they work by being reducing agents. They sacrifice themselves, getting oxidized easily, to protect other important molecules in our cells from being damaged by oxidation.
That's fascinating. So what's the big takeaway for us? Why group these together?
Because mastering both acid-base, proton transfer, and redox, electron transfer chemistry, is absolutely fundamental. It lets you understand why your stomach digests food, acids, how batteries power your life, redox, why metal rusts, redox, why buffers work, acid-base equilibrium, and even how your body functions at the most basic cellular level, both. Yeah. These aren't niche topics. They connect to practically everything, from fire to breathing to making materials.
Okay, powerful stuff. Now, we've talked a lot about bonds within molecules, covalent, ionic. But what about the forces between different molecules? You mentioned them briefly with water, but these intermolecular forces, or IMFs, they seem crucial for explaining the actual properties of matter we see, like why something is a liquid or a solid.
Yes, you've hit on a really critical distinction. We have the strong forces inside molecules holding atoms together, the chemical bonds. Then we have the generally weaker forces between separate molecules, the intermolecular forces. They might be weaker individually, but cumulatively, they have enormous effects. They dictate whether a substance is a gas, liquid, or solid at a given temperature. They determine boiling points, melting points, viscosity, surface tension, and why some things dissolve in others.
So what kinds are there? Are they all the same?
No, there's a hierarchy. The weakest type, but universally present, are London dispersion forces, or LDFs. These exist between all molecules and even individual atoms, regardless of whether they're polar or not.
How do they arise if a molecule isn't polar?
It's due to the constant motion of electrons. Just by chance, at any given instant, the electrons in a molecule might be slightly more concentrated on one side than the other. This creates a temporary, fleeting dipole, a tiny separation of charge. This instantaneous dipole can then induce a similar temporary dipole in a neighboring molecule, leading to a weak, short-lived attraction.
Ah, like a momentary static cling?
Kinda, yeah. They're weak individually, but they add up. They become more significant for larger molecules with more electrons, because there's more sloshing around possible. This is why larger nonpolar molecules, like waxes or oils, which are big hydrocarbons, can be liquids or even solids at room temperature, while small nonpolar molecules like methane, CH, or helium are gases. The LDFs are just stronger for the bigger molecules.
Okay, so LDFs are everywhere. What's stronger?
Next up are dipole interactions. These occur specifically between polar molecules, molecules that have a permanent separation of charge, a built-in positive end, and negative end. The positive end of one polar molecule is attracted to the negative end of its neighbor. It's a stronger attraction than LDFs for molecules of roughly similar size because the dipoles are permanent, not fleeting.
Okay, polar molecules stick together better.
Generally, yes. And then there's a special, extra strong type of dipole force, hydrogen bonds.
Ah, we talked about this with water. What makes it special?
It's specific. Hydrogen bonding happens when you have a hydrogen atom that is covalently bonded to a very electronegative atom, specifically nitrogen N, oxygen O, or fluorine F. That bond is highly polar, leaving the hydrogen very partially positive. This very positive hydrogen is then strongly attracted to a lone pair of electrons on an NO or F atom in a nearby molecule.
So it's H bonded to NO or F, attracting another NO or F.
Exactly. It's significantly stronger than typical dipole forces.
And this explains water's weird properties.
It explains so many of water's properties. Water molecules form an extensive network of these hydrogen bonds. That's why water is a liquid at room temperature. Look at similarly sized molecules without H bonding, like hydrogen sulfide, H2S, or methane, CH. They're gases. Water's strong H bonds hold the molecules together tightly, requiring a lot of energy to pull them apart into a gas, hence its unusually high boiling point, 100 degrees C. It also explains why ice floats. When water freezes, the hydrogen bonds arrange the molecule into an open hexagonal lattice structure that actually takes up more space than the liquid water. So ice is less dense.
That's counterintuitive, but makes sense with the structure.
And hydrogen bonding is absolutely critical in biology, too. It's what holds the two strands of the DNA double helix together. It dictates the complex folding patterns of proteins, which determines their function. It's fundamental to life.
Wow. Are there any other IMFs?
One more important one is ion dipole forces. This is the attraction between an ion, like Na, U, or Cli from dissolved salt, and a polar molecule, like water. These are quite strong, often stronger than hydrogen bonds, and they are the reason why ionic compounds, like table salt, dissolve so readily in polar solvents like water. The polar water molecules surround the ions, stabilizing them and pulling the crystal apart.
Ah, okay. That explains dissolving salt. So the big picture here for you, the listener, is that the strength of these intermolecular forces directly impacts macroscopic properties. Stronger IMFs mean higher melting points, higher boiling points, higher viscosity.
Exactly. Compare methane, CH, only has weak LDFs, boils at minus 164 degrees C. Compare that to water, H2Os, similar size but strong H bonds, boils at plus 100 degrees C. That's a massive difference, almost entirely due to the IMFs.
Incredible difference.
And these forces also explain the like dissolves like rule. Polar substances tend to dissolve in polar solvents because they can form favorable dipole or hydrogen bonds. Nonpolar substances dissolve in nonpolar solvents, interacting via LDFs. Oil and water don't mix because their IMFs are incompatible. Yeah. And ultimately, IMFs determine the states of matter. In solids, IMFs are strong enough to lock particles into fixed positions. In liquids, IMFs hold particles together but allow them to slide past each other. In gases, particles have enough kinetic energy to completely overcome the IMFs and fly around freely.
So this idea really bridges the gap, doesn't it, between the invisible world of single molecules and the tangible stuff we interact with every day.
Precisely. It explains why ice floats, why liquids flow, why oil and water separate, even how geckos can stick to walls that involve specialized intermolecular forces too.
Okay, now let's think about a chemical equation. It shows reactants turning into products, the start and the end. But if we want to understand the process better, how does that transformation actually happen? What's the step-by-step story at the molecular level?
You're asking about the chemical reaction mechanism. That's exactly what it is, the detailed step-by-step sequence of molecular events that transforms reactants into products. Reactions very rarely happen in one single giant leap where all the reactant bonds break and all the product bonds form simultaneously. That's usually too complex and energetically demanding.
So it's more like a series of smaller steps.
Exactly. Reactions typically proceed through a sequence of simpler steps called elementary steps. These steps often involve forming short-lived, unstable species called intermediates. These are molecules that are produced in one elementary step and then consumed in a subsequent step, so they don't appear in the overall balanced equation. The pathway also involves passing through high-energy, fleeting arrangements of atoms called transition states. These are like the very peak of the activation energy barrier for each elementary step.
Example.
Sure. Let's say the overall reaction is nitrogen dioxide, NOO, reacting with carbon monoxide, CO, to form nitric oxide, NO, and carbon dioxide, CO. The mechanism might involve two steps. First, two NO euromolecules collide to form NO and an intermediate. Then that NO and intermediate collides with a CO molecule, reacting to form NO, and the final product, Co.
So the NO is made and then used up, and one of the NO molecules is regenerated.
Exactly. The mechanism describes that actual molecular dance.
And this mechanism, it has to line up with the kinetics, right, with how fast the reaction actually goes.
Absolutely critical connection. The experimentally observed rate law, how the rate depends on reactant concentrations, must be consistent with the proposed mechanism. Often, one step in the mechanism is significantly slower than all the others. This slowest step acts like a bottleneck.
The traffic jam analogy again.
Right. We call this the rate-determining step or rate-limiting step. The overall speed of the reaction can't be faster than its slowest step. So the rate law for the overall reaction is often determined primarily by the molecularity, the number of molecules involved of that rate-determining elementary step.
Understanding the steps can explain why the rate depends on certain concentrations and not others.
Precisely. And it can also explain why certain products are formed. For example, in some organic reactions, the mechanism might involve an intermediate that's flat, planar. Reactants can then attack this intermediate from either side, leading to a mixture of different 3D spatial arrangements or stereoisomers in the product. The mechanism explains the outcome.
And this is where catalysts fit back in too, isn't it? They change the story, the mechanism.
Yes, exactly. Catalysts work their magic by providing an alternative reaction mechanism, a different pathway from reactants to products. And the key feature of this alternative pathway is that it has a lower overall activation energy than the uncatalyzed pathway.
A lower hurdle, but a different route.
Right. They don't change the starting point reactants or the ending point products. The overall thermodynamics remains the same. They just provide that faster, easier route. Think about enzymes again. They often bind to the reactant molecules, called substrates, in a specific way, stabilizing the transition state for the reaction, thereby dramatically lowering the activation energy and speeding things up. We also see other complex mechanisms like chain reactions. These often involve highly reactive species called radicals molecules with unpaired electrons.
Radicals, like an ozone depletion.
Exactly. The depletion of the ozone layer by chlorofluorocarbons, CFCs, is a classic example of a catalytic chain reaction involving radicals. A single chlorine radical, CLER, generated from a CFC molecule by UV light can initiate a cycle. It reacts with ozone, producing KLO and ORO. Then the KLAO reacts with an oxygen atom, regenerating the original Cl radical and forming another ORO.
So the chlorine radical gets reused.
Over and over again. That single chlorine radical can destroy thousands, even hundreds of thousands of ozone molecules before it's removed from the cycle. That's the devastating power of a catalytic chain mechanism.
Wow. Okay, so the deep insight here for you, the listener, is that knowing the mechanism is incredibly powerful. It moves beyond just balancing equations. If you understand the step-by-step molecular route, you gain the ability to control the chemistry.
Yeah. You can find ways to speed up a desired reaction, maybe by choosing a catalyst that facilitates a key step. Or you could slow down an unwanted side reaction, perhaps by adding something that intercepts an intermediate. You can even steer a reaction towards a specific product by understanding which pathways lead where.
So pharmaceutical chemists designing drugs rely heavily on mechanisms.
Absolutely. They need to understand how a potential drug molecule interacts with biological targets at a mechanistic level.
And environmental chemists figuring out smog or ozone depletion.
Need to unravel the complex atmospheric reaction mechanisms to understand the problem and find solutions.
It really feels like this is where chemists become molecular engineers.
Yeah.
Right? Rationally designing and manipulating reactions based on the pathway.
That's a very good way to describe it. Understanding mechanisms gives you that control.
Okay, final big idea. Chemistry is often called the central science. And based on everything we've discussed, that seems pretty accurate. It bridges physics, biology, geology, materials science. These core chemical principles don't just stay in the lab. They are literally the foundation of life, and they power countless technologies we depend on.
Absolutely. The applications are just vast and fundamental. Take biochemistry and medicine. The chemistry of life itself relies on all these principles we've covered. Enzymes are biological catalysts. Their function governed by kinetics and mechanisms.
Right.
How your body breaks down glucose for energy. That's cellular respiration, a complex series of controlled redox reactions, releasing energy based on thermodynamic principles. the very structure of DNA, with its double helix held together by hydrogen bonds, the intricate 3D folding of proteins, essential for their function. That's all down to chemical bonding and intermolecular forces. And medicinal chemists use this deep understanding to design drug molecules that can specifically bind to target biomolecules, like a faulty enzyme modulating its activity to treat a disease. It's targeted chemical intervention.
Amazing. What about the stuff around us? Materials.
Materials science and engineering is completely enabled by chemistry. Understanding chemical bonding and structure allowed us to create synthetic polymers, plastics, nylon, Kevlar, materials with properties nature never made, semiconductors, the heart of all our electronics. Silicon chips require incredibly pure silicon, precisely doped with tiny amounts of other elements to control its electrical properties, grown into perfect crystals. That's all sophisticated chemistry.
Right, the chips in this device right now.
Exactly. Advanced ceramics, superalloys, all designed based on understanding structure-property relationships at the atomic and molecular level. The lithium-ion battery powering your phone, a marvel of applied redox chemistry and solid-state chemistry, carefully balancing electrode materials and electrolytes. Even something seemingly simple like vulcanized rubber, making it tough and durable by cross-linking polymer chains with sulfur, was a major 19th century chemical innovation based on understanding molecular structure.
Okay. And what about large-scale industry?
Industrial chemistry and processes are the engines that feed materials and chemicals into almost every other sector. We mentioned the Haber-Bosch process for ammonia several times, synthesizing ammonia from nitrogen and hydrogen for fertilizers. It's estimated that roughly half the current world's population is alive today because of the increased food production enabled by this single chemical process.
That's staggering. Half the population.
It really is. And these massive industrial syntheses are triumphs of applying chemical principles, equilibrium, thermodynamics, kinetics using catalysts, high pressures, specific temperatures, all optimized to make the process efficient and economical. And now, the modern push for green chemistry is applying these same core ideas, but with an added focus. Designing processes that minimize waste, use less hazardous substances, and are more energy efficient, using chemistry to solve chemistry's own problems.
That's crucial. And finally, energy and the environment.
Energy and environment are perhaps the biggest challenges where chemistry is absolutely central. Burning fossil fuels for energy is combustion, a redox reaction with major environmental consequences, ORO emissions. Developing alternative solar cells, photovoltaics involve semiconductor chemistry, better batteries for energy storage, electrochemistry, fuel cells, controlled redox reactions all relies heavily on chemical innovation. Understanding atmospheric chemistry, like the mechanisms of smog formation or ozone depletion we discussed, is essential for diagnosing problems and formulating effective environmental policies. And chemists are working hard on solutions like carbon capture technologies, using principles of gas solubility, absorption onto materials, or acid-base chemistry to trap CO before it reaches the atmosphere or even pull it back out.
So, the ultimate takeaway for you listening to this is that chemistry is truly inescapable. It's fundamental. From the food you eat, the clothes you wear, the medicines you might take, to the air you breathe, the water you drink, the energy powering your home and devices, chemistry is right there at the heart of it all.
It really is.
It gives us the power not just to explain the natural world, why does ice float? How do plants make sugar from air and water? Questions people wondered about for centuries. But also the power to create the modern man-made world, from concrete and steel to plastics and computer chips to purifying water.
It's both explanatory and creative. That's its power.
Well, we've certainly gone on quite a journey today. A real deep dive into atomic structure, how molecules connect, how energy flows, how fast reactions happen. We explored the genius of the periodic table, that dynamic balance of equilibrium, those fundamental proton and electron transfers in acid, base, and redox, and even how those subtle forces between molecules dictate the properties of everything we touch.
What I find truly fascinating, and hopefully you do too, is how deeply interconnected all these big ideas really are. They don't exist in isolation, do they? They constantly build upon each other. Atomic structure explains bonding. Bonding and IMFs explain properties, thermodynamics, and kinetics govern reactions. It all weaves together into this incredibly comprehensive and, frankly, elegant framework for understanding matter and its changes.
Yeah, elegant's a good word.
And this integrated understanding, this chemical literacy, is what continues to drive incredible progress in science, in technology, in medicine. It empowers us to innovate and to tackle really complex global challenges in health and materials, in energy, in the environment.
So, maybe this raises an important final thought for you, the listener. Now that you have this perhaps deeper understanding of these invisible forces and principles at play, how many of these big ideas can you actually spot in something as seemingly simple as making toast in the morning? Or maybe in the air conditioning, cooling your room right now? How does knowing about atoms, bonds, energy, rates, how does that change how you see and interact with the everyday world around you? Does it make it more amazing, more understandable?
We really hope this deep dive helps you feel more informed, definitely more curious, and maybe just more engaged with the incredible chemical world that shapes every single aspect of your life. So keep observing, keep asking questions, and yeah, keep exploring.